Hey guys, in the next few videos we're going to discuss a really unique type of elimination reaction called the Cope elimination. So guys, it turns out that amines are really easily oxidized, even by weak oxidizing agents. In fact, if you just leave some amine in your bench at the laboratory and it's exposed to open air, even just the O2 gas that's in room air is enough to oxidize amines into hydroxylamines and even amine oxides, okay? And it turns out that tertiary amine oxides are capable of doing something called a self-elimination and making an elimination product, specifically a Hofmann product. Now, it might have been a long time since we did elimination, but hopefully you guys can remember there was a Zaitsev product and a Hofmann product. The Hofmann product being the one that was the less substituted. Okay, so we're going to be forming less substituted elimination products through a Cope elimination. Now, there's a little bit of theory you want to get into beforehand, just in case you read it in your textbook. At least I explained it to you one time. So it turns out that, first of all, anything that is a tertiary amine oxide can also be referred to as an N oxide. That just makes sense. You're saying that there's an oxygen coming off of an N, okay? That would be, basically, let me just circle it for you. That would be this kind of structure right there. So you got an O directly attached to N. But what we notice is that there's a really weird type of bond there. Notice that I have an arrow pointing to the O, which is something that we don't really talk about a whole lot in organic chemistry at the college level, right? But that contains what's called a dative or a dipolar covalent bond. So what does that exactly mean? Let me just define that in case you forgot or in case you've never heard of this before. It's a covalent bond. So that means that there is equal sharing of electrons. It's a strong bond. It's covalent just like any other covalent bond you learned about. But we call it dipolar or dative because you've got two charges that are separated on that bond. Okay, you've got a positive and a negative. Notice that they never go away. So you got your positive, you got your negative, and it's known as dipolar because one of the species is the one that's giving its electrons away to the other. In this case, we know that the nitrogen has a very, nucleophilic / basic lone pair. So it's going to go ahead and donate that lone pair to the oxygen, forming that dative bond. Now, it could very well be denoted just as a straight line. Because as you guys know, covalent bonds are always just drawn as a stick, right? So you could just draw it as a stick, that would be fine. But in some texts, it's denoted as an arrow. So it would be nitrogen, arrow, oxygen, which for the purposes of this class, I just want you to recognize as a bond. This is going to be a covalent bond just like any other bond. All right? Awesome. So now I just cleared that out of the way so we can talk about the reaction and the mechanism. So first of all, before we go into the mechanism, let's just look at the general reaction. What we've gotten is an amine that we're first going to oxidize. This is hydrogen peroxide. So hydrogen peroxide, not the strongest oxidizing agent, but I just told you guys, even O2 gas, just room air, is enough to oxidize an amine. So definitely hydrogen peroxide can, okay? What you're going to form is that dative tertiary amine oxide, or the N oxide. Now, what's special about these guys is that N oxides can self-eliminate. So what we're going to wind up getting is, in heat is going to wind up separating these, and you're going to wind up getting a Hofmann alkene. Okay, so you can see that basically we had two options. We could have either gone in the red direction here or in the blue direction here. We went with the less substituted version, so that's Hofmann, and you wind up getting a hydroxylamine as a substituent. I mean, not as a substituent, as a byproduct. I'm just going to write here this is a byproduct. We don't really care about it. Okay, so now in the next video, what I'm going to do is I'm just going to break down the Cope elimination mechanism, and then we'll do a practice problem.